So on behalf of Mike Newman, Heather Heidenreich, our friends from AIA Chicago, including Laura Crane and Andre Lopez from the Young Architects Forum, and myself, I'm Mark Tier of Black Spectacles. We'd like to welcome you to today's A.R.E. webinar, Solving Structures Problems. And sort of like the last one, this is also a really exciting event because it marks our second A.R.E. webinar, which we've hosted. But it's really our first one at a Chicago architecture firm. So we'd like to thank Matt Dumich and our friends here at Adrian Smith and Gordon Gill for hosting us here at this amazing space. So thank you guys very much. Today's event, as you know, is a collaboration with the Young Architects Forum. Again, thank you, Laura and Andre. But this event is a supplement to our online A.R.E. curriculum, which we've built in collaboration with Mr. Newman here and AIA Chicago. Our online curriculum is kind of an offshoot, if you will, of the in-person workshops that Mike and AIA had been doing for many years. And then we basically took those workshops and we built and kind of reworked a brand new online curriculum. That's basically a bunch of video tutorials that covers all 7 of the exams in both the multiple choice questions as well as the vignettes. So it goes really in depth into all of them. And it's nice because you can sort of, you can kind of watch them wherever you want, whether you're at home or, commuting or at work or whatever. So we're going to continue, our plan is to continue hosting these online webinars as well as in person. And our next one is going to focus on the schematic design vignette. So we'll provide a link at the end so you can be sure to sign up for that session too. And for those of you, of course, attending in person, we'll all meet after the session downstairs at the Berghoff at 17 West Adams for drinks and to, share A.R.E. war stories. And we hope all of you online can at least, have a beer while you're listening. We'll go for about 45 minutes, and we'll take about 10 or 15 minutes for questions. And we'll take those questions from everyone here. And then if you're online, you can either use the GoToWebinar chat box, or you can send your questions via Twitter using the ARE4 hashtag. Just tag them that way and include @BlackSpectacles, and we'll queue those up for our Q&A session. So for today, as you can see, Mike brought reinforcements. He brought Heather Heidenreich from the Chicago office of KJWW, who has 14 offices all over the globe. They're an international engineering consulting firm who specialize in healthcare, higher ed, K-12, commercial, government, and industrial buildings. And their expertise is in designing sustainable and high-performance building infrastructure systems for mechanical, electrical, technology, structural, and architectural lighting. They've done a lot of great work here in Chicago, so you are certainly in great hands. Heather is a structural engineer. And for those of you who don't know Mike, he's been an architect and teacher for almost 20 years in Chicago, working on a wide array of commercial and residential projects. He's taught everything from design studios to systems integration to architectural theory. He's currently teaching at the School of the Art Institute of Chicago, and his practice is named Shed Chicago. He also has been teaching and coordinating seminars for the A.R.E. since 2004, and of course, most recently with AIA Chicago and Black Spectacles. So with that, I'll hand it over to Mike and Heather.
Okay, well, as Mark said, welcome. One of the first things to say about working on any of the structures problems, this is the thing that I just want to make sure we hammer home right off the bat, which is don't fret about it. It's all going to be just fine. One of the things that happens is that architects tend to sort of, their eyes glaze over and they start getting panicky, and they start thinking that, oh my gosh, this is going to be something I can't handle because it's calculations. But in fact, most of the exam is actually about concepts. It's about basic understanding of sort of rules. We're going to go through a couple different types of problems. We're going to do some more concept-based ones and then a few calculation-based ones. But you should know that the calculation-based ones even those, the formulas generally will be given to you in some form. What you're really looking for is kind of a general understanding that you can recognize the formulas, be able to plug the information in, but also sometimes you don't even need to do the calculations. It's really just about kind of a basic, clear understanding of kind of what's going on. And one of the things that I always like to say about this is stuff that you actually know already. The hard part about it is that you have to translate it into sort of engineer speak. You have to translate it into sort of the structures world of how things are talked about. So as we're going along, Heather will, being the structural engineer that she is, she will talk in kind of engineer speak, and when it feels right, I'll try to help translate that back and forth. But in general, that's the kind of way you should be thinking about this. This is that it's not anything that's outside of your basic understanding. It's really just trying to find the right language to be able to talk about it, and therefore to know what steps to take, what to do next. Because that's always the big question. So let's just sort of dive right in, and we will start off right off the bat. You'll notice that we gave you a few helpful hints along the way. We gave you some formulas. That's the kind of thing that would show up on the front of the exam. And we also, in the middle of some of the questions that we had sent out to everybody before we started, we have some charts and things because you can use those along the way. So these are some of the formulas that we might come reference back to. But let's start in with the first one. So on our first one, the question is, where in the beam shown is the moment the highest? So Heather.
Right. So you can use intuition a little bit on this particular problem because as you can see by the dimensions of where the loads are located, that everything is symmetric about the beam. So by intuition, you can figure out what the reactions on each end are, and they are going to equal 3 kips apiece because I just took the 6 kips total that are applied to that beam and divided it in half because of everything being symmetric. Now, if you feel comfortable and you can go intuition-wise and keep going that way, you will ultimately come to the answer that the moment is highest right here at midspan. But for those of you that don't feel comfortable doing that way and want to do a little bit of the math behind it, we're going to show you how you can get there. So the thing that'll get us there is we're going to draw the shear diagram here for this beam, where
I've always been curious why you use V for shear, but that's one of those engineer speak things.
So we're going to start by doing a shear diagram, and you're going to go up. You're going to follow your loads. So we're going to go up 3 kips, and because we don't have any load applied, we're going to go straight across, and then we're going to come down 2 kips. Must be my hand that does this. So we're going to come down 2 kips, and then we're going to go across again till we hit that next load, and we're going to come down 2 kips, which takes us across the 0 line and puts us at -1. And then we are going to go straight across, and then down 2 kips, straight across, and then close it up with that last 3 kips. Now, the one thing to know about your shear diagrams is whenever that shear diagram crosses 0, so this point right here, whenever that happens, that is your maximum moment.
So when that shear diagram crossed the 0 line, that we essentially have just answered the actual question right there. Like and it happens because this one is symmetrically loaded. It happens to be right in the middle, and you could have guessed that beforehand if you'd sort of been thinking about it. But this is sort of a clear description of why that's the case.
Correct. Yep. So if we move on to the next question,
well, why don't we go
do
ahead
you
and
wanna do?
let's draw the moment diagram.
Okay, so let's do that. So
just for fun, because
exactly.
What could be more fun than drawing the moment diagram?
So yes, we are going to draw that moment diagram, and you need to know a couple of different things that I'll describe along the way. The first is to figure out what number you're going to go up to. We're going to do the area underneath this shear diagram. So we basically have a 3. We went up 3, so this value here is 3. And you're going to do the area of it. So it's 3 times 3, so it's 9. And whenever you have a straight across, so a box shape in your shear diagram, you're going to get a diagonal line in your moment diagram. So we're going to go up to 9, and then you're going to keep doing your math where you have, this is 1, and it's 6 feet long, so we're going to go up another 6 to the center. So we come up to 15.
So you were kind of doing those in those, you're just kind of separating those out as different boxes. So the
Yes.
first one was the 3 kip amount by the first 3 feet, and then you jump to the next box, which was 6 feet long, but only 1 kip high.
Right.
And so you're kind of just adding it
Yep.
up as you go along.
Yep, and then because we crossed the 0 line, these are all negative, so we're basically going to come down those same numbers. So you're going to come down a total of 6 to the +9, and then you're going to come down the rest of the way down to 0.
So that just to be clear, that line probably shouldn't have been so straight looking,
Yes.
but there you go. And one of the ways to think about this that I find useful, not everybody finds useful, so if this confuses you, just forget about it, but that the slope of the line on the moment diagram is equal to the value of the shear diagram at that moment. So if you think about that, in that shear diagram up there, that first 3 feet, you have a value there, and there's a specific slope, and that's going to be a relatively steep slope. And then in that second box that we talked about for that next 6 feet, it's a lower number on the shear diagram, and so it's a lower slope. And this will become sort of more useful when you look at the next example, but this is one of those things where you start seeing there's this direct set of relationships, and you can do a whole series of calculations. We could have done this through sums of vertical and moment sums, but in fact, you can actually do this fairly quickly just by kind of graphically kind of playing it out.
Correct. Yep.
Why don't we go to the next one? So this is another very similar question, but this one's a little more complicated.
Yep. So intuition is only going to get me so far in this one because it's not symmetric, and I have 2 different load types. I've got a distributed load, and then I've got this concentrated load over here. So I need to figure out what my reactions are first to even attempt figuring out what my shear diagram is going to look like to figure out where my maximum moment is. So the way I like to do it is I'm going to sum about this left-hand side right here. And to do that, we're going to basically be summing a moment about that point. So to do that, we are going to look at the different direction the loads are going. So we are going to start out with the 1.5, and it is acting over 12 feet. And then you want to look at it and say, what's its moment arm? So its arm here basically is half of the distance it acts over. So it is another 12 over a half, so it's 6 feet.
So the first 1.5 times 12 is actually the total load that you're talking about.
Correct.
So the 12 foot is, because it's 1.5 kips per foot, in order to know what that total load of that particular one, you have to multiply it by the 12 feet, but then the moment arm is the half of that distance.
Mm-hmm. Correct. And so keep going with the next set of loads. So the 1.5 kip per foot is going to act in the same direction as that 4 kip load, and it is acting 15 feet away from this left end. And when we do this, all of this has to sum up to 0, because otherwise we don't have a static beam here. You don't want your beam galloping down the road.
Yes, flipping around.
Yeah. So I'm going to call this other end here B, just to give us a value. But it is acting in the opposite direction that the other 2 loads are. So it's going to have a minus sign. And it is acting at, let's see, that's 6 and 12. That's 18 feet. And when you solve for B, it actually comes up to 9.33 kips. And then you can sum your forces in the vertical by saying this 4 kips plus the 1.5 times 12 to get it to a total load, and then subtracting off the 9.33 gets you to the reaction over here, which is 12.67. So when we draw our shear diagram here, we're going to start doing it the same way we did the other. So we're going to go straight up because we've got that 12.67 kip reaction, but we have a distributed load, so you got to treat that a little differently because every foot you're taking off more load. It's not like this concentrated load where it happens all at once. So because it's a distributed load, it actually is going to have, and I'm just going to draw some guidelines in here for myself because that's how I do things. So because of that, we're going to have this diagonal line that continually changes value every foot as you go, because you're going to subtract off that 1.5 kip every foot of the length of that 12-foot area that it acts across. So once you hit that, we see that there is no load then between the end of the distributed load and the concentrated load, but then you hit the concentrated load and it goes down a little bit more and then goes straight across and comes back up. So now we have seen that here's our point of maximum moment, because that's where it crosses zero. But we have to figure out what it is. And so there's a couple of different ways you can do it. I like to use similar triangles just because it's graphic for me, and that's what I like to do. So I have one triangle that I know it's 12.67 over some unknown value, but then my other triangle has to be the whole thing, where it's the total of 12 feet down here, but then it's 12.67 plus the 5.33. I've done a little extra math for you here, but it's the sum of that, and then when you solve, you can basically then do your ratios and solve for x, and you get a value of x, which is 8.45 feet. That's how far away from this left end that point of zero shear is.
And so that tells us our basic question, which was, where is the highest amount of moment?
Correct.
And we figured that out through a combination of using the shear diagram, understanding kind of what the shear diagram was telling us, and then doing a kind of a quick version of what, kind of a fast graphic version of helping us understand where exactly that point of crossing is. But we also could have done a moment diagram. We could have done a sum of moments and then figured out distances. Like there's a series of other things we could start to figure out as well.
Yeah, I guess the one thing that this helps you is, yes, you could have drawn that moment diagram, but if you're feeling crunched and frantic because of time, don't feel like you have to do that. By knowing that your point of zero shear is your maximum moment, you've saved yourself some time.
But just because we're narcissists like this, let's go ahead
right.
and show that, just to have a moment to discuss what these things look like.
Yep, so now again we have to think about that the point of moment is based on the area underneath this. So, and I haven't done this math, so I'm not going to really put values down, but I'm going to draw what the diagram looks like.
Yeah, so this is just sort of approximate.
Yep. So basically, because we have now a sloped line in our shear diagram, the line in the moment diagram needs to be a curve. So it's going to come up here and it's going to peak basically right there.
And we happen to know that because we've already figured that out.
Yep. So then it's going to start coming back down on a curve. Oop. Bad curve.
Bad curve, but a curve, okay.
Yep. So, but then when you hit this point where the diagonal stops, you've hit basically a constant slope line. So now you're going to get a straight line.
So a diagonal straight line,
Yep.
just like the previous one that we were doing.
Correct. Get one of those, and then you're going to get an even sharper one. It's difficult to tell from my very crude drawing.
Yeah, so not the greatest drawing on them, but there you go. And once again, the version that I was talking about, again, just find the system that you feel comfortable and how to think about these things. But if you think of it as that the value of the shear diagram is telling you what's going on the moment diagram, as that sloping line goes, the value is dropping at every point, and you can see that the curve, that's the slope is changing and becoming closer and closer to zero until it gets to that maximum point. So same kind of thing. So whatever system you find that helps you kind of see these things or be able to just think of them graphically, that's what you're looking for. So okay, we asked people to send in some examples. And so I'm going to jump over to an example answer, and we'll see how. This one's from Spencer, and we'll see how Spencer did. Okay, so on the first one, looks like Spencer got that the first one pretty spot on.
Mm-hmm.
And in fact, his drawing looks a little better than ours. So there you go. And let me try taking a look at the next one. Oop. Sorry. Okay, here's the next one. And
so we got the reactions right, and I mean he didn't draw the shear diagram, but it looks like he got the end value, so it looks.
Yep, it all looks
good
pretty good. So you can see all calculations there, and he's summing all the forces. And again, this is one of those things you don't necessarily need to do the moment diagram in order to understand where the maximum moment is, as long as you understand the relationship between the moment diagram and the shear diagram, which obviously is also related to the loading diagram. Okay, way to go, Spencer. All right, let's go back to the things here. All right, and going on to problem number 2. Okay, so problem number 2, you were working on a hospital in Japan in an area of high seismic risk. At a preliminary design review, there are various concepts being considered. Which is the most sensible approach? So, okay, Heather, we've got a couple different things. We've got an 8-story L-shaped building. We've got a 6-story symmetrical plus-shaped building. We've got a square building, and then we've got the rather restrictive, you should not build a hospital in a seismic zone. What do you say about the L-shaped building?
Well, the L-shaped building could work. It has one piece to it that we don't like as much as the rest, and that is this little inside corner here. I think that if you imagine grabbing this end here and grabbing this end here and wanting to move them back and forth, you'll see that this spot right here just kind of wants to rip apart right through there. And so that, not that you can't build this way, but it wouldn't be my favorite choice.
And you'd have to put a lot of extra structure in there in order to do that. So what you're essentially saying is that each of those wings is going to start shaking on its own, and they're going to kind of crunch into each other at that inside corner. If you really like this choice, I would probably say that I want to build it this way, where you see a joint between the two. And so they can they have a way to move separately and not hurt each other.
Exactly.
How about the plus? Well, the plus is going to be obviously the same thing, just 4 times, right?
Yep, exactly. The plus has a lot of and basically what we call these inside corners are re-entrant corners. And from some of the handout material that you sent out, there are some code tables that were pulled together, and so it's kind of one of those things that we have to design around and make the structure more robust. So we're spending more money on structure instead of all the pretty architecture. And that's what we like, pretty architecture. So if you look in the problem set handout, there's a couple of sheets in there that give a little bit more information about re-entrant corners and things like that. So obviously we're coming down to it. C is clearly the answer. You're talking about a square-shaped building. And the reason for that is just because it's all going to move as one? Yeah, and it's symmetric, so we love symmetry. For seismic issues? Yep. So it allows us to be, ideally we'd want to put something on each of the outside edges. So it allows us to be centered, if you will, about where the mass of the building is going to work, and that's usually about pretty close to the center of a square. So yeah, our choice would be the square. And one of the things you'll find is that often on the exam there'll be things that will say something like, you should not build this or do that. And those are not usually sort of logical answers. They may seem logical at different points, but you can always do it. It's just a matter, as Heather was saying, like where do you want to spend the money? And since the exam is often about the idea of efficiency, this is sort of a good example of just like the D is just not a reasonable answer in this context. All right, let's move on to the next one. So these are the code tables we were mentioning. Right, so these are in your handout. There's a couple different code tables that you can look at. So here's question number 3. So question number 3 is, the contractor is about to place the concrete for a complicated but important structural wall, but something seems a bit off and you are worried. Which concrete test would you look at first for reassurance? And then we have a couple different answers. We have hydration test, core test, slump cone test, cylinder tests, and penetration test. So the key thing here when you're reading this question is that time seems of the essence, that something's wrong, and before things get too set in place, you want to, are things going reasonably correct? So a couple things we can do right off the bat is we can get rid of a few of these choices. So one that we can get rid of is A, because hydration test I just made up. So that's not a real thing. Maybe it's a real thing. I don't know. Maybe it is. But I made it up either way. And then core test and penetration test, those are things that you would do down the road. Yeah, like the core test would be something you do on an existing structure to figure out what your strength of concrete might be. Right. That'd be one way to do it. There was something that was going wrong and you wanted to test it out, or maybe it's an existing building and you're trying to see, can you add more load to it or something. Right. So the core test is a real thing, but it's just not something you would do in the way that the question was described. And I think the penetration test is sort of a similar thing. So really the two that are the sort of main ones that you're likely to be asked about would be the slump cone test and the cylinder test. And the slump cone test is where you just have this sort of cone-shaped formwork piece, and it's about 12 inches tall, and you put a bunch of the concrete from
a particular truckload that's coming in, it's about to go into place, and then you flip the cone over and you lift the cone off, and you just sort of see how much does it slump down. So if it had a big slump and it like puddled, let's say it slumped down 10 inches or something, that means it's probably way too watery. And it's going to have cracking problems. It's going to have sort of the capacity is going to be lowered. Or let's say it didn't slump at all. Let's say you're on a job site and it had a 0 slump. Well, the problem with that's going to be it's going to be hard to get any of that like in and around the rebar. It's going to be hard to get it to between the rebar and the formwork, or if you have a complicated formwork setup, which this question specifically says, a 0 slump would be very, very difficult in that situation. There are places where 0 slump is quite useful and happens all the time. For example, in precast, where you have a lot more control over how it's being placed. But this is an on-site kind of question. So the slump seems like it's telling us quite a bit, and it's telling it to us right away. So that's one possible answer. How about the cylinder test? So on the cylinder test, what happens?
Yeah, so these are a lot of times they're plastic cylinders that they'll just scoop some of the concrete out as you're pouring it into these, and they're supposed to let them cure on site so that they match what the concrete is out in the actual form. But these are usually broken at 7 and 28 days, so if you're going to know anything, you're going to have to wait for 7 and 28 days. So if you're needing immediate answers, the cylinder test isn't going to give them to you.
Yeah, because they're trying to. I mean, what happens with most cylinders that get done on a job site is they get put. They're supposed to cure in the same place so that you get the same climatic conditions, but eventually they just get put into a basement somewhere and labeled, and a year later somebody throws them out. Actually, probably nobody throws them out because they're big and heavy, and like, why would you want to do that? And so they just sit there forever. So they're not really used, but they are very useful if something has gone wrong and you're going back to check. Like, wait a minute, so there seems like there's a problem. Therefore, let's check the trucks 5 through 7 that had their load that went to this one wall, and you can go back, find the label, and then you literally smash them, and that gives you an opportunity to check that, like what kind of pressure it took to smash that, and therefore you know what happened. Well, that's great, but that's, as Heather says, that's 28 days later, maybe 7 days later. Like, you might do an early test because you can get a pretty good sense of it, but it's probably way later. So the way the question was worded, it's talking about, I'm worried, I want to find out what's going on. The slump test is definitely a more useful one for you in that context. And I can guarantee you there'll be questions about slump tests and cylinder tests somewhere. I'm not sure how it'll be worded, but there'll be something because it's kind of a key one.
Right.
How did Spencer do?
Let's take a look and see what happened with Spencer. I'm going to have to bump forward a couple here, but let's see how it goes. So let's see, you got the square building, and
Spencer got it right.
Yes. All right. You're doing great, Spence. All right, so let's jump on to question number 4. So question number 4, this one's going to take a little bit of calculation. Question number 4, the framing plan shown is for a 2-story simple light manufacturing building. If the loads are as follows, axial loads only, live load of the second floor is 80 PSF, dead load of the second floor is 20 PSF, live load of the roof is 30 PSF, dead load of the roof is, again, 20 PSF, and then we're going to ignore that first floor slab on grade, just because it's sort of being held up by the ground below. So we have 2 basic questions here. The first one is, what is the total load of the column that's been indicated? So what's the first thing we need to figure out?
Well, the first thing that you need to know is that there are all these loads, so we're going to add those up in just a moment. But the big thing to understand is how does the load even get to the column? So the big key word is tributary area here.
Tributary area,
Yep.
Yeah, it's a key word and it'll show up somewhere.
Yeah, so basically we are going to have half of the bay in each direction, and I'm just going to draw a square here for you. That this is basically the trib area that column is going to see. So basically half of the 25-foot bay in each direction and half of the 30-foot bay in each direction is going to contribute to the load that goes down that column. So we know that the area, I'm just going to keep it easy for you, is the 25 and the 30, and we're going to multiply it by our load, and I'm going to do some addition in my head. So 80 and 20, that's 100, and another 50, so that's 150.
So you could do this where you actually did the second floor load and then did another one for the roof load, and then you added them together. What Heather's doing is just sort of putting it all into one one thing and
Since
saying.
we just
so
wanted the load at the bottom, I did a little
If
shortcut.
you add them all up and multiply that by the area, that's going to be the 150
Yep.
PSF.
So right now, if you notice though, you want your answer in kips, and right now all my units are in pounds. So you will have to divide, for those that maybe aren't as aware, you have 1,000 pounds in one kip, so we will have to divide this whole thing by 1,000. But our final answer here is 112.5 kips is what comes down that column.
And this is one of those things that you have to definitely be watchful for, because while they're not generally trying to go out of their way to confuse you or be mean about it, there often are answers that if you didn't notice the word kip in that there would be a version that would be very close in pounds, and so it's kind of taunting you to choose the pounds one even though it says kips. You have to be really careful about matching kips and pounds, matching feet and inches, matching all of those kinds of issues show up all the time on this. Units are a huge deal. So the answer is, the first part of the answer is 112.5 kips, but then that leads us to the second question, which is if the soil below that column is capable of 4,000 PSF, what is the size of the footing? So that means the 4,000 PSF is referring to the soil capacity.
Right.
Like if you put a load on that's more than 4,000 pounds per square foot, presumably it would start to settle or some problem would start to happen. So how can we make sure we're being safe? What kind of area do we need to be able to handle that, that load?
So when you're figuring out the area of anything and you have a pressure, so we basically know that a pressure equals a force over an area. So we know P and we know that pressure, and we're going to search for A. So by rearranging this equation, we're going to take the load and divide it by the pressure. So I wrote out the load up here in pounds so that you can see what we're going to get for an answer up here. And I wrote out the units longhand so that you can see how when we do the math that you're going to get an answer in feet squared. When you do this math, it ends up being 28.1 square feet.
So there's an interesting question. Now our answers are 4 times 7 feet, 4 feet times 7 feet, which is 28 square feet. Mm-hmm. That's pretty darn close, but there's two problems with that. Problem number one is, well, it's 28, it's not 28.1. So you actually are a little bit less than what the requirement was. What's the other problem with 4 times 7?
Well, it's rectangular, which you can do.
There might be a reason why you would have to do it. But since it doesn't tell us anything about, like, we're up against the property line or something, like, why would you want to do that, right?
Nope.
So the fact that it's not symmetrical, it's going to be, it would be harder to get the rebar in there to figure out how to make that work, to spread it out. It just doesn't make any sense. But the 29 square feet, that sure looks pretty good because that's just bigger than the 28.1. So that's really the answer. Mm-hmm. Some folks may have seen a different possible answer. So tell you what, let's take a look at what our submitted one said.
Yeah, let's see what they liked.
If I can get this to work. Oh, there you go. It's all Heather's problem. All right, here we go. So on this answer, they chose 6 by 6, which is an interesting answer because, like, that's often on the exam there will be more than one correct answer, and in my mind, I think the 6 by 6 is a correct answer. It's just not as correct as the 29 square feet answer, and the reason I would say that is that, anybody who's actually done concrete work knows that, if you start giving people an answer like, yeah, the footing should be, 5'2" and 5/8
Yeah,
inches.
they don't build to that.
They just don't build to that. It's just not how concrete works. And so generally you're going to round up, and you're going to round up to maybe a 6-inch line, or maybe a foot line, something like that. Maybe, if you're being a little more tight and controlled, maybe it's to every 2 inches or something. But like a 6-inch thing would be sort of fairly typical. So I could imagine that if our answer is really 28.1 square feet, and then you start thinking, well, how big is that? And like if we did 5 by 5, is that big enough? Well, no, that's 25 square feet. So
Right.
it's not 5 by 5. It's the next one. It's 6 by 6. So it's a reasonable answer, but it's just a little too wasteful in the context of the exam. If it had said 5'6" by 5'6", then it'd be a closer bet, and
Right.
I think that might be a reasonable answer. I think the 6 by 6 is just a little too far off, but you can see why they answered it this way.
Yep, and looking at D as an answer, it's the math. It just has a
Right.
units issue in
It's
it.
just
so.
a unit issue, right? Because that's
Yep.
yeah, exactly. That's one there to taunt you to do it wrong. All right, let's go on to the next one. Okay, so this is on number 5. You're in the middle of the SD part of the schematic design part of the set, and the architect realizes that the zoning height limitations may be a problem, and therefore must get a reasonably accurate typical floor-to-floor height for the design on a mid-rise office building, presuming a 1 kip per foot loading, and that the beams are 20 feet long. And you are likely to use A50 steel. What wide flange would you use? So, okay, there's a couple of things. For one, we have to do some quick calculations.
We do, yes.
And then beyond that, we're going to have to do some other stuff as well.
Yes, we are. So let's just dive right on in. So one of the equations that you're going to need to know is moment for a simple span beam with a uniform load, and you've hopefully come across this once in your lifetime, but it's WL²/8 is the moment equation.
And like I said, most of the time the formulas will be given to you, and you don't really need to worry too much about it. Like, you can actually find them. But there are going to be some that are probably worth just memorizing, just to have it in the back of your head. And this would be one of those ones, because
Yeah.
it just shows up enough, and, why make it more complicated?
So now we're going to just do the math, and we have this happening, and you end up getting, I believe it's 50 if my notes read correctly. Yep, so we have a moment of 50 kip feet, and we have some critical information that before we flip to the next page, which will help us pick our beam size, it tells us we're going to use A50 steel, so it's 50 KSI steel, and it also says that we're fully braced laterally, which means that you don't have to worry about not choosing the best beam that you possibly could, because it's nicely braced. So,
Which a typical beam in a situation like this
Yeah.
would be.
Yep.
So, yeah.
so if we go into the charts, hopefully those of you that are with the actual printout can look at this and read it a little easier than you might be able to on screen. But we're going to want to use, so here's where we said the grade of steel was a little critical to know. So if you look at this, the gray shaded section is actually where you'll see the 50 KSI steel. So we want to pay attention to the gray shades. And then I drew over top of it, but this third column right here has MR, so that's the moment that we need to find. We need to find a number that reads above 50. So on the right-hand side, you see that we max out at 47, so we're going to keep going and come down here to the right, or the left-hand side.
The bottom of the left-hand
Yeah,
side.
and we see 50 right here at the bottom, and I just drew right over top of it. But we do see 50 show up, so we at least know that this 8 by 21 beam will satisfy our load. But one of the things with the beam chart here is you'll notice that the beam sizes above it some of them are lighter. So you actually, while this 8 by 21 works, it's not the most efficient shape. This top one actually is an M shape, so we're just going to jump to the one right above it. But we get a 12 by 19 is the lightest beam that hits that 50K.
So here goes the sort of the key thing of understanding about the wide flanges and the idea of efficiency, especially as regards the exam. When you're talking about structures, you talk about efficiency, you're essentially talking about dollars. Well, how do you understand dollars in steel? It's about weight. And since the wide flange, the first number is the nominal height, the second number is the weight per linear foot. And so if it's a higher weight per linear foot, it costs more. That's straightforward. It will always be the case that unless it is specifically asking you about height issues, then the choice will always be to go with the lighter weight example for the wide flange. As long as it's not outrageously different in terms of height, but it's always about that lighter weight. Now, this is kind of a little counterintuitive for a lot of the architects out there, because if you start to imagine say a 3-inch difference or something like that, and let's say it's a multi-story building, and so I'm now adding 3 inches at every floor, I could very easily have actually a very inefficient choice that way. Like, it could be in the real world that maybe I'm adding, if I go with a lighter version, but it's 3 inches taller, that I might be adding, say, 12 inches to the building or 15 inches to the building, at which point I'm adding 15 inches of brick all the way around the building, and 15 inches times the area of the building in terms of air conditioning, and et cetera, et cetera. There's lots of reasons why I might choose to go with the heavier but shorter in terms of depth beam. But in terms of the exam, unless it specifically is asking you that, it's guaranteed that they're looking for the lighter weight beam. Mm-hmm. So the way these charts are done, and I don't know if they'll show you a chart like this, but it kind of just sort of gets you used to thinking about how these things work. The way these charts are done is they group them together in sort of logical groupings, mm-hmm. right? So that in each of those groupings, like that on the bottom left-hand side, there's 4 grouped together. Those all kind of meet roughly the same capacity. Correct. But some are heavier, some are lighter, and they're in order in terms of sort of how you would think of them.
Yep.
So there you go. All right. Let's move on here.
So this is just another way that we look at them in the steel manuals, just to let you know.
It's a different version of.
Mm-hmm.
And then this is about columns, which we'll talk about later.
Mm-hmm.
Okay, so number 6, which is most likely not to have camber built in? And then our choices are composite deck, double T, open web steel, LH joists, wood glue lam. So the first question here is, what the heck is camber?
Yeah, so camber is a natural crown, kind of like this picture over here shows, where the piece isn't going to come out flat. It is going to have an upward bend to it. And one of the reasons why we like that is if you think about some of your long spans, if you start out flat, it's only going to keep deflecting downward. So we like to start with an upward crown. That way when you start loading, get your roofing on a big stadium or something, it'll bring it down a little bit, and then you won't have
right, so
ponding issues when it wants to rain and
right.
sit
So
on
it starts crowned upward, mm-hmm. and then by the time it actually gets real loading, it loads into flat-ish.
Right.
And some are more crowned than others. It kind of depends on the situation.
Correct.
But the concept of camber is that idea of the crowning it up a little bit.
Right.
So then the question is, all right, of these, which ones are often crowned? So let's jump to double T for a second. What the heck is the double T?
So double T is this shape over here where it's got 2 stems and a flange.
Okay, and
it's
so
made out of precast.
That's a precast
typically.
Concrete, and the place you'll often see these things is like there'll be single T's, there'll be double T's. You'll see them in parking garages, mm-hmm. and stuff like that. And they're pretty robust structures. I mean, they can span pretty far, and they can take a pretty big load, and they're often used in these things where you don't mind having seams, like a parking garage. So they're pretty big deal. Like what would be a typical span of one of those things? Like, I don't know, 40 feet.
I've done them up to
60
100.
feet. Yeah, so like 60 feet is probably pretty typical. 100 feet's starting to get pretty long, but you could certainly do it. Mm-hmm. And something like a precast concrete, that's totally going to have camber built into it.
Yep.
Because it's just begging for it, right? Because it's going to have creep over time. It's going to keep deflecting.
That's the whole purpose too. I mean, it gets tensioned in the plant, and so as you release the tension, the tendons, and you cut them to a shape, when they release, they're going to pull inward, and
Right.
so it just wants to pop that middle up.
So what she's saying is that when they pre-stress these things, so while it's being cured, they have these steel tendons that run through it, and they pull them really hard, and then when it all cures, that's what's creating that that camber up. So definitely the double T is going to have camber.
Yep.
And then let's take a look at the open web steel LH joists. Those are long span joists, and the LH is what's telling us that. And those are absolutely going to have camber, same kind of thing. The camber is going to be built in because that's, for example, Heather's example of putting the roofing on, something like that. Those are fairly light structures, and so in order to give them a little bit more capacity, you put the camber in, and then when it gets that roof load on it, it's going to settle down into essentially the correct slope for the drainage of the roof.
Right.
So then the real question is between A and D, composite deck versus wood glulam. What do you want to say about the wood glulam?
Well, wood glulam is a manufactured product, so if you wanted to put a camber into it, you certainly can. It's an easy material to put camber into.
Because you're making it up, right?
Yep.
I mean, it's one of the ways that you can give that wood glulam that little extra boost of capacity is by building in that camber, and then when it does deflect, because it is wood after all, it'll deflect some. When it does deflect, it'll deflect to flat, and so while it won't necessarily happen every time, sometimes wood glulams are used more decoratively than they are for serious levels of structure. But when you talk about a glulam, you're generally talking about a pretty serious structure generally, and it's very likely to have camber. So therefore, we are left once again here with A, the composite deck. So tell me about the composite deck.
So a composite deck is the fluted material that you're going to put on top of your actual structure, which is a lot of times beams. And we don't like to roll deck. It's a difficult material to roll. So that's why if you were just looking at these, I would ask myself, which of these can I actually camber? And this one pops immediately into my mind that while you could camber, it's very difficult to camber. But one of the things to be...
And it would be hard to judge how much you would camber it.
Yeah. One of the things, though, to be not confusing in this is a composite beam system typically does have camber in the beams because you are a lot of times having lighter beams.
Because you're getting the benefit out of the concrete in the deck.
So while it's under a wet condition, it needs a little bit of oomph to not deflect and have this big ponding situation in the concrete.
So if this had said not a composite deck, but a composite beam system, then that also could have had camber in it, but because it was just talking about the deck. So, that may be a little bit of a cheat. I don't know. I think it's a reasonable response.
Yeah.
So shall we take a look at...
Should we see how Spencer did?
How Spencer did. So let's see here. So this is the previous one. Let's look at this. Yep, you got composite deck. So he's
just
batting almost 1,000 here.
Yes,
so that's
he's
awesome.
Doing quite well.
All right. So let's jump to question 7.
Okay.
All right. So question 7. You have a wood structure, and the engineer says that the horizontal shear stress capacity of the 2x12s is lacking, but you don't trust her. I wonder who we could be talking about. As she has been on Facebook.
Not me. I have been on Facebook.
As she's been on Facebook during the entire conversation. You decide to check for yourself. If the highest shear stress allowable for Douglas fir larch is 180 psi, then does this loading work? And so we have a beam here. It's intriguingly symmetrically loaded.
I love it.
So tell me about it.
Okay, so we need to think about what is the shear through this beam. So the maximum shear through a beam like this is going to be at its end span. So by seeing that it's symmetric, I'm just going to use my judgment and say that it has 1 kip of reaction at each end of the beam. And from there, so that's our shear. But now we have to figure out how much shear stress we have. So that's going to be an equation that unfortunately in wood is a little different because of this first factor I'm going to put in front of you. But let me write out the whole thing first. So in wood, because you are dealing with a material that is looking at a horizontal shear, and because your point of worst shear is actually when you go vertical through the section and you're trying to split apart those horizontal grains. And so that's where this 3 has, it is a lot of differential equations in converting a vertical shear into a horizontal shear. So this is just a factor you have to remember in wood, and it's specific only to wood. But then we're still going to do the normal load over area.
And if this was on the actual exam, they would definitely give you that
Yeah.
somewhere. Might be in the front of the exam, might be in the question somewhere, but that formula would
Yep.
definitely be there.
So now we're going to basically finish filling in the equation. So again, I told you that this was a constant, and we know P, we know that that is 1 kip, and then we can figure out the area of a 2x12. You've got to go back to thinking about what the dimensions
So
are.
here's the whole important thing to remember. This is one of those things that used to get drilled into every architecture student in the country, but I know has sort of slipped by a lot of folks these days. A 2x12 is, it's nominally, it's named a 2x12, but it's not 2x12. It is in fact 1.5 by 11.25 inches. So a 1.5 by 11.25 is what a 2x12 is. If we were talking about a 2x4 or a 2x6, it would be 1.5 by 3.5 or 1.5 by 5.5. But the 8s, 10s, and 12s all go to the quarter. So a 2x8 is 1.5 by 7.25. 2x10 is 1.5 by 9.25. And in this case, the 2x12 is 1.5 by 11.25. Like, that's one of those things you just got to memorize them because it'll show up in lots of places.
Yep. So we know that our allowable shear stress is this 180, but I wrote the load down as 1 kip. So we do have to multiply by that 1,000 pounds per kip to get our answer. When you do the math here, you get 89 psi, and when you compare it to the 180, you are actually under, so the 2x12s actually have enough shear capacity.
So look, there you go. All right. Let's jump on to the next question. Okay, here's a question about columns. And this is sort of a general question. This one is just saying, all right, the current design development, the current DD set, the current design development design, calls for a 10-foot tall W10 by 33 column in a building that you are working on. And the question is, what are the most important elements for understanding what the maximum allowable load would be for that? So imagine you sort of have an assumption, you put it into place, and now you're trying to like, well, okay, what are the issues that would be at play here? So we've started with a couple little sketch images there to help us along. What would you say the basic worries here would be?
Well, the first thing you want to think about is what is the contribution to figuring out the capacity of a column. And so you are really thinking about, is it tall and slender? Is it short and squatty? And you may have heard this little equation here, KL over R. And so the different parts of this actually are what are the most important pieces to be thinking about. K goes up here to these diagrams. It basically is having you think about what are my end conditions. This first one shows a pin-pin. The second one is a flagpole kind of condition, so it has a fixed base. And then the third one shows you 2 fixed ends. And
so because the 2 fixed ends, it means that as they come out of the fixity, they're coming out at 90 degrees.
Correct.
Unlike the pin, which can rotate around, and
Yep.
So you get a very different curving happening.
Right. So the value changes as you go through these. I happen to know that this pin is a 1.0, and I believe the cantilever is a 2.0.
Yeah.
This one I have no idea off the top of my head.
Yeah, we'd have to look it up.
But you can see how they change, and so depending on what fixity you have.
And if we look at our little diagram, what fixity do you think we have?
Yeah, that looks like a pin.
Yeah, that's sketched as a pin. It's not the best sketch ever. Sorry about that, but that's meant to be a pin connection. So that's definitely the K is 1.0 on that.
Yep. So then the next piece is L, and that's your height over here. So that certainly is going to contribute. So if you're shorter or taller, it makes your number here bigger. And basically, to have a good capacity for a column, the lower this K over R value is, the more capacity you'll have in your column.
Right. So like one of the ways to think about this, that one of the big advantages of thinking of the KL over R is the big question on a column when you're doing calculations on a column. There's a couple different ways that a column can fail. one of the ways the column can fail is through buckling, and one of the ways the column can fail is just that the material fails, like steel or concrete or whatever it is, just it has so much load on it that it just fails. And so, but then which ones are which, and which times do you need to use the formulas for buckling, and which times do you need to use the formulas for the capacity of the material, the robustness of the material itself. And so if you start thinking about it, if you just sort of exaggerate it in your head, if instead of that being a 10-foot column, if you said, all right, what if that's a 100-foot tall column? Well, if that's a 100-foot tall column and we're putting any load on it, are you ever going to put a load on it in such a way that you're going to crush the steel? Probably not. You're going to buckle that column way before you're going to crush anything. All right, well, on the converse side, let's say instead of being 10 foot tall, it was 1 foot tall, and we put a whole big load on it. Really, you're going to buckle a 1 foot tall steel column? Like you're never going to buckle that, but it might, if you put enough load on it, crush the steel or rip through it. So clearly, there are a bunch of situations where you are going to focus on the material issues, and there's a bunch of situations where you're going to focus on the buckling issues, and then there's some in the middle where you probably have to do calculations for both because that's, it could be either, it's not clearly one or the other. So it's kind of a triage system. You're kind of breaking it into the triage, and that's one of the things that the whole K/R starts to help you sort of think through, is getting you to the spot where you're deciding which of those formulas. So that means that what we're trying to figure out here is, well, we need to know like how tall it is, what kind of connections there are, in this case the pin connections, and therefore that's going to lead us to how that K/R is going to work. And then the other thing we would want to know would be more about the W10 by 33, but we can look that information up, and in this case that's the R, that radius of gyration.
Yeah, so if you go to a bigger W10, the R value is going to go up, so that'll help bring the K/R value down and give you more capacity, like we were saying. Right.
So the big issues, the height, the connections, in this case the pin connections, and then the sort of, I don't know how to say it other than robustness of the shape, the kind of what that's telling us. Let's take a quick look and just see what our
polars from home, how they did.
Yeah, so, okay. Let's see. So he's saying tributary area and radius of gyration. So tributary area is not a bad thing. What that's saying is that the area that is going to contribute load to that column would be a significant thing I'd want to really think about. So that's kind of getting into the loading of the area and how much load per square foot we probably have versus the shape itself. So I think that's a reasonable answer as well. And then obviously radius of gyration we just mentioned. I would also include though that I think that the pin connection is really key. And then obviously we've given it as the length, the 10 foot, but I think it's worth mentioning it as well. All right, let's jump back into our issues here. Okay, so we're on 9, and 9 says, does the wood 3x6 beam work for deflection with the loading shown? And then it says the E, which is the modulus of elasticity, for Doug fir is 1,900,000, and then it gives the moment of inertia for the 3x6 as 34.66 inches to the fourth.
Yeah. So this is fun stuff.
There you go. This is an exciting one. So check out that formula over there.
Yeah. So here is your deflection formula. It's 5 WL to the fourth over 384 EI, and I know it looks like it's a little crazy, but it's not too bad. We can plug everything in and take a look at what the result is. So the 5 and the 384 are constants. That's just part of the equation, but we're going to fill in the rest of it. W is 500 pounds per foot. And then L is 15 feet, and it's to the fourth. And then we're all over the 384 and the 19 million. And what wasn't told is that's actually in PSI, so that's pound per inch squared. And then we were given I, which is the 34.66 inches to the fourth. Okay, so this formula is notorious for having units issues. So you can kind of see the top is all in feet, but the bottom is all in inches. So we've got to do some conversions here. So if you go back to the days of doing ratio, thinking about your fractions, we're just going to start crossing off what cancels each other out. So the pounds cancel each other out. This inch to the squared on the bottom is going to cancel 2 of the 4s over here. This foot on the bottom is going to cancel 1 of the feet there. So you get feet cubed over inches squared, and we know that the answer is going to be in inches. So we need to convert this baby right here. We're going to convert that feet cubed to inches. So we know that we have 12 inches per foot, and it is going to be cubed so that we get these feet to take these feet away. So we get inches cubed over inches squared, which in the end will give you inches. So when you do the math, you will get 8.64 inches, which is not a lovely number.
So let's think about that for a second. This is a 15-foot beam, a 3 by 6 wood beam that's 15 feet long, and its deflection is 8.64. That's almost 9 inches. That's way too much deflection.
I'm not going in your house if that's
that is my house, actually. That's about the same deflection in my house. Clearly, if you had, drywall and plaster would be cracking and breaking, and if you had bricks or something on top of that beam, it would all the mortar would be broken. Like, that's just way too much. So maybe what would be a typical relationship that we would try to get?
So we use 2 different ones. There's one that's L over 240, and then there's another one, L over 360. This one here is usually used for total load, so you're dead plus live, and then this one over here is usually used as for live only. Those are our kind of rules of thumb. There are times where we will use other values. For masonry we use something different, but these are your pretty typical ones.
Yeah, so these are the numbers you'll see. If you see it on the exam, it's going to be probably one of these 2. And it'll tell you either for the total load or for the live load, and then it'll give you one of those numbers. But what that's essentially saying is that the total length, you divide it by 240, and that the number that comes from that is the sort of allowable deflection that you're going to be able to go for before it's going to start to crack and do other problems.
When you actually do figure out the L over 240, it's only 3/4 of an inch.
Right, which kind of makes sense if you think about it. Like, 3/4 of an inch is still a fair amount of deflection. But, things have to move a little bit. If you have a big load on something, it's going to deflect a little, and that's, the materials are built to be able to take that. They just can't take something like 8.6 inch deflect. That's just way too much. But if that number had come out to, say, 1/2 an inch or 5/8 of an inch or something, it'd be fine. Even if it came out right to 3/4, it'd still be fine. But then there are some very specific situations where you could imagine a question where it's much more higher tolerant. Because there's a very particular need, like the masonry or something, but the vast majority of them are going to be either this L240 for the total load or L over 360 for the live load.
Correct. Yep. So knowing that we have so much deflection, the easiest ways to change those is to figure out what's in that denominator and make those bigger.
Do you have a question about, could you redo how you did the units again, how you converted the units?
Oh, yeah.
So question about the units.
Yeah. So basically when I did the units, I wrote them out all longhand so that I could see what I had in each fraction, if you will. And then I just started using the rule of fractions where if it's in the top, you're going to multiply by 1/, to get it to cross out. And so I was just trying to cross out the different pieces.
And so you're doing that both fractions that are within the numerator
and
as well
within
as
the denominator.
But as well as then also between the numerator and the denominator.
Correct.
So it's happening at both levels, within the formula and also the overall formula.
Yes, that's very true.
That's one of those things. You do it a few times and you'll get reminded of it, but it's a tricky.
Yeah, it takes a while.
Takes a while to get used to that. And this is one of those ones that is always problematic like if you're going to have trouble on units, it's going to be in a deflection one because it's just sort of a nature of it. But before we move on, let's take a quick second, just sort of talk about this formula a little bit. Like this thing can seem very, very complicated, and they may ask you to do a full calculation out. But it's also possible that they may ask a question that you can actually answer just from understanding the issue here. So let's say, for example, we just figured out that this particular example just is just not strong enough to handle, and it's going to have way too much deflection. So what could we do to fix this problem?
Sure.
So there's a couple different things we could do. We're looking at that formula. any one of those numbers, the 5 and the 384, all gotta stay because those are constants. But we could mess with the W, we could mess with the L, we could mess with the E, we could mess with the I. So let's start with the E. Like, what could we do? We could go to a different material that had
Sure could.
a different modulus of elasticity.
Yeah, steel is going to be much stronger than that.
So if we went to a steel in place of this wood, that the modulus of elasticity for that is going to be significantly higher, which means that denominator is going to be higher, which means that the deflection, that the overall fraction, is going to be much smaller.
Yep.
So going to steel would be one way to think about this. We could also, the 3x6 is a sort of reasonable shape, but with the I, we could also go with just maybe a much deeper section. Like maybe it's still wood, but maybe it's a 4x12 or something like that. So it has a much deeper element, and then that I is going to be much larger, and then again, the denominator is going to be larger, and therefore the overall fraction is going to be smaller, so you're bringing down the deflection amount. And same thing goes with the W and with the L. That we could say, well, okay, this is all fine, but you just can't load it to 500. You got to find some way to bring that W down, which I don't know how you do that, but that's a way you could think about it. But the other way to think about it is maybe the L is wrong. Like maybe there has to be a column halfway in between, and so you're actually, instead of being 15 feet, it's 7.5 feet or something like that, right? So very quickly, just once you understand what those letters are standing for, you can actually answer a lot of questions that would be about, well, what would you do if this was the case? Right.
Mm-hmm. Yep.
All right. Let's take a quick look at what our
friends at home.
Friends at home, what our respondee said. So this one, we look at number 9 here, and we see that the got the L240. That looks good. So figured out the 0.75 inches, the 3/4 of an inch. And that first run, 5 over 384. So everything in that first line looks pretty good, but came out with a different number.
Yeah, so we think there might just be a bit of maybe a calculator error. I know my fingers get fat sometimes, and I punch the wrong button.
Yeah, so I'm not exactly sure what happened there, but everything, all the setup looks right, but then something's not quite right in the final follow through. It might be maybe it's a units thing, but I think it's probably just a calculator error. All right, let's jump back, and we'll go on to our last one here. All right, so this is for number 10. For the belled caisson with the soil boring report shown, calculate the axial loading bearing capacity for this foundation element. Assume the topsoil is organic material and provides no bearing capacity. So we have here a belled caisson shown in section, and then the bearing capacity of the soils, all the different levels of the soils from the soils boring report. That starts off in the top level, has topsoil, and there's some silty sand that has a 1200 PSF capacity. Then we have sandy gravel, which has 2200 PSF down below that. Then there's a couple of mixed ones, gravels and sands and silts and such at 2900 and 3200. And then down there's bedrock at the bottom there at 10,000 PSF. So which of those numbers are we going to really care about?
Well, I don't know about anybody else, but if I'm going to put a caisson in, I want a nice big number, so I like the bottom one.
Yeah, essentially this is total red herring. All of this extra information, the only one you care about is that 10,000 PSF down at the bottom. All of those other silty sands and all that stuff might be useful for a different foundation system if you were doing a raft or a spread footing somewhere higher up. But the entire point of a belled caisson is you're reaching way down to get to some very good soil, hopefully bedrock, although not always. And then you're going to bell it out. You make that shape at the bottom where it's a column of one size for most of it, but then when it gets down to the very bottom, it gets wider. And the whole point of that is just to get more bearing area down at the very bottom, so you're not having to do a full 8-foot column all the way up, and that would be a huge amount of concrete. And so you do the 4-foot column. In this case, it's 4 foot, lots of different sizes. And then bells out to the 8-foot down at the bottom. So the question then is, all right, I've got the 10,000 PSF, and I've got an 8-foot bell down at the bottom. What's my capacity?
Yep, so your question might be a little confusing because it does
Quite likely.
have the word bearing capacity in there. So some people may think that it's this 10,000, but it's actually wanting to know how much axial you can put down the thing. So if you remember from a previous problem, we know that pressure equals P over A, and we're actually going to solve for P. So we want to take that 10,000, and it's, let's see, it was PSF, I think, is what you're giving everything in. So we know it's 10,000 PSF times the area, and so it's the area of that circle down here at the bottom. Down here, we want the area of that. So I'm going to write it out in terms of diameter, but it is pi r squared. I tend to think in terms of diameter too much today. So that's how to convert it to, so it's...
I totally would have done a pi r squared, but okay, yeah, we got you. So the 8 over 4 is...
So when you do the math, let's see, where's my cheat sheet here? When you do the math, you get 500, you can write it as 502,000, you can write it as 502 kips. So that's the answer.
The answer there is that's what the total capacity for that size of a beld caisson on that capacity of bedrock with the 10,000 PSF, that's what that's going to tell you. So you're doing the area and then the capacity of the soil, and that's telling us what the potential P is, the potential total load that we'd be able to design for whatever this building is.
Yep.
And this is the kind of thing you have to be very careful of, that just because they give you a lot of information doesn't mean it's pertinent. So this would be one of those examples where a lot of red herring information.
Mm-hmm. Do we have any questions in the...
Yeah, there's a question here. It's about just in general, with the structures exam, there's lots of, are there going to be a bunch of problems? Is it going to be, just a few? Like, can you sort of talk about how the structures exam kind of lays out?
Yeah, so the question is just about the overall, how the questions work overall. And one of the things you'll find when you take the exam is the calculating questions will loom large in your head because they're just sort of out of your normal, they're not what you typically do in the day. But in actuality, there's probably only a relatively small percentage of ones that you actually have to do a lot of calculation on. Remember, you have to move through these things pretty fast, so the calculations have to be fairly straightforward and simple. You have to be able to do a question in maybe less than a minute, certainly. So anything that seems like it would take much longer than a minute probably isn't likely. You're probably going down the wrong path. And there's probably some way to answer it without actually doing the calculations. Many more of the questions, a much higher percentage of questions, will be on things like the seismic question that we talked about, something like that, where it's sort of a general understanding of how things move in a seismic situation. Or it might be in a sort of efficiency question about, what would make the most sense in a given situation. Would it make more sense, like let's say there's a very detailed manufacturing place that's it's like an iPhone manufacturing something, where they're doing very specific and detailed manufacturing and they don't want a lot of vibration. Well, what kind of structural system would you suggest for that? And you could think, well, wood? No, probably not wood. Steel? Well, steel is awesome, but it vibrates a lot. Mm-hmm. So, which is one of the great things about steel is it has a lot of ductility, but that may not be the right choice there. So maybe if it was something like that, it's probably concrete, some sort of concrete thing. That's a kind of question that's very, very typical of the sorts of questions you'd get on the exam, because it's about the whole point is just trying to check, can you have a reasonable conversation with a structural engineer? That will you be able to understand what they're telling you? Will you be able to kind of go through the information and make kind of rational decisions, but also not get pushed around by a structural engineer? So
pushy us? I don't think so.
So that a question might come up, and then the structural engineer has like the way that they've done it before. Well, that may not be the appropriate thing for your project. So it's just trying to check to make sure, can you actually have a reasonable conversation with a structural engineer? And so most of the questions are going to be focused on kind of those sorts of basic conceptual understandings, and then a good I don't know, 10% of them will be very simple calculations, and then maybe another 10 or 20% will be a little more complicated calculations that you have to actually kind of spend some energy on. But it's one of those things where, like I said, if it's taking you longer than a minute to answer the question, probably just move on. Doesn't there's no advantage to you to spend 5-10 minutes answering a single question.
The other question we have is, will the answers to all these questions in the work that you did, Heather, will that all be made available?
No, it's top secret.
It's all top secret. Yeah, you better have taken notes. No, we will be making available all the calculations that Heather just went through. So you'll have access to that on the site somehow. I'm sure Mark will make that available to you. Yeah, so absolutely, and you can also, of course, look back through the video and sort of watch it live again. All right.
Anyone else?
That seems like it's the last of the questions. So let's just take this moment and say Heather from KJWW, Heather Heidenreich from KJWW in the Naperville office, thank you so much for helping us out.
Welcome.
And KJWW is a great engineering firm, all kinds of different engineering help they can give you. So please check them out if you need some help. I will say so long. This is Mike Newman. I'm going to hand it over to Mark Tier, and he's going to talk to you about the end product here.
Yep. So thank you, Heather and Mike, and of course, thank you to Mr. Matt Dumich and our friends here at Smith-Gill. Thank you so much for hosting us. Our next webinar, as I noted, will be on the schematic design vignettes, and that'll be in September. We'll post a link for that because we are just finalizing the exact date and the firm that will host it. If you go to our website, and if you go to our blog, so blackspectacles.com/blog, and if you choose the webinar tab on the right side there, you should easily find the next one when we post it. We'll also post it along with the video. We're going to record this and post this on YouTube, so it'll also be included in the description there as well. So again, thank you again, and we'll see you at our next webinar. Thanks for tuning in.